And please. So, hi everyone. Today we're very happy to have our own Miguel give a talk about atomic and molecular physics and curve geometries. AMO physics and curve geometries. Thanks so much.
Thank you, Nima, for the invitation. It'd be my pleasure to come back to the High Energy Physics Journal Club to give a talk. So these are some topics that I am currently interested in doing some research on and exploring, because you're going to see that the connections are quite unexpected, and I think they just show the beauty of these curve geometries. So what is some of the motivation that AMO physicists have to look into curve geometries? Well, first, we all are hunting basically for the perfect system to do quantum simulations on. And AMO physics has been one of the nice and interesting settings in which those systems can be implemented. They have a manageable size and they can be studied in the lab. So in terms of the relation with curve geometries, it would be more precisely when we're looking for systems where we can do simulations of gravitational systems, where we can look into some of these interesting ideas that theory has come up with that relates geometry and entanglement, as well as testing the holographic principle and some of the other area laws. This has also arisen as kind of a substratum where we can implement fast scramblers, which could give insights into the dynamics of information inside black holes. There's also this whole field of analog gravity, where there has been some experiments in both Einstein condensates where sonic black holes have been implemented. So there's a lot of things going on. In this talk, we're going to focus on two studies, two separate studies. One of them, the two of them are related to curve geometries, but they arise in a quite different way. The one on the left here, which will be the first, is a very nice experimental result that shows how curve geometries can emerge if you tune the interactions between a very simple quantum mechanical system, and you can see this hidden geometry through the study of the correlations. And the second one, which will be kind of the bulk of the talk, is going to be the analysis of this system, which is a system composed of superconducting circuits. So it's like circuit QD, arranged in a very specific pattern that resembles the hyperbolic space in the Poincare disk. And what we will show is that you can describe this with a quantum field theory or a continuum theory on the continuum geometry. So we'll see that the lattice theory can be described almost exactly by the continuum theory. So why don't we start with the engineering interactions and the emergent geometry. So we'll start with a very interesting experiment. I know, please don't run away. The interesting math will come shortly. Where we put a string of atoms in a one-dimensional trap like this, where we have a driving laser represented by this sinusoidal here that mediates interactions between them. We, on top of that, also put a magnetic gradient so that the hyperfine splitting between the atoms makes these different spin states have different energies depending on the location of the atom in the magnetic field gradient. The interactions between the atoms are going to be spin exchange interactions, and you can modulate whether it is paramagnetic or ferromagnetic by assigning a different sign to the interaction between the two sides. So what the people in this experiment measure are the correlations between the two sides, and this correlator will define it shortly. And they can relate that to the different types of interactions that you have. And this shows the importance of having the magnetic, that magnetic gradient that makes the spin exchange a non-resonant effect. So for instance, in this first slide, in this first image here, you have monochromatic, like this driving laser, but you don't have a magnetic gradient. So they're like all the atoms can talk with one another and exchange spin. On this side, you again have a single monochromatic driving pulse, but you have this magnetic gradient turned on. So you effectively turn off the interactions between different sides of the lattice. And if you turn on the driving laser with different frequencies, which we will see are the space between these frequencies is given by essentially the separation between these two hyperfine states, what you find is that you can actually tune these interactions. So for instance, you here have the central space token only with the limiting spaces in this one-dimensional array just by introducing these three extra frequencies. So the Hamiltonian of the system is essentially this. You have like these balls that I was showing before. They are actually clusters of atoms indexed by these Greek symbols. And this is the racing operator in the spin, in that triplet spin system that we saw for each atom. This is just the Zeeman quadratic effect given by that magnetic gradient that we had in the previous slide. And then the strength of these correlations between spins is going to be given by this pulse, in which this WB is just the splitting that we saw before. So essentially, by making a pulse that has the right Fourier transform, we will be able to tailor these interactions. And then the correlations that we will be discussing are two. First is this kind of magnetic correlation where you measure the number of atoms that have a spin +1 inside I, and then you compute the correlation with the number of atoms that have spin -1 inside J, and then you take the average over the site, over all the sites that are separated by a given distance, and then you can create these matrices that I was showing before, where the correlations depend on the distance between the two atoms. Another type of correlations that we will be interested on are these aligned spin correlations, where you basically measure the total spin in each one of these sites. So each one of these sites is composed by a lot of atoms, and then you take kind of the macroscopic magnetization in each site, and then you compute the correlation in a specific axis. Here they chose the x-axis, and then the way that this interesting geometry arises is by assuming that these correlations will behave as a Gaussian with some coordinates in a hidden coordinate space that we will extract. And essentially the way that coordinate system is found, where this strange geometry lives, is essentially obtained by taking the singular value decomposition of this matrix of distances given by the correlations.
Sorry, Miguel, can I?
Yes.
So at each side you have a qubit in practice. Is that right? Is it a two-level system? Is it?
No, it's a tree-level system.
It's
here
a
they
tree-level system.
Atoms with tree. So by inducing this magnetic field, the sites with spin -1 and 1, they follow the Zeeman effect, right? So the spacing will grow, but the zero level stays the same in each site. And then you have a lot of atoms in each one of these red bubbles.
And so you basically can, this way in practice, in principle, you can engineer any interaction, right?
Right. Mm-hmm. By tailoring the amplitude of each frequency. So if you see, each frequency is just a multiple of the spacing between the energies. And then if you tune the amplitude that corresponds to a given separation, you are engineering the interaction between that separation in this one-dimensional line.
Okay, so here n is what exactly? N plus of I, what is the operator?
Oh, that is the total, the number of spins with value 1. So
So it's like,
the number
yeah,
operator.
it's SZ, well, I see, I see.
It's like the number of spin with m the number of atoms with m equals 1, I guess.
Okay, okay, thank you.
Sure. And then if we explore different configurations for the poles, so I have not shown the poles here, but each one of these cells corresponds to a different poles configuration. You can see that the interactions are tailored different. So for example, here, what they've done is that they have just induced ferromagnetic interactions between neighboring sites, like first neighbors, and they, on top of that, induced periodic boundary conditions in the lattice. So this one-dimensional string of atoms is composed of 17 sites, and they have essentially made nearest neighbors with periodic boundary conditions. And if you go and see what is like the geometry hidden inside this correlation, you see that it is the same geometry that you can derive from this. And it is manifestly different from the physical geometry of the array of atoms. For this other one, what they have done is like they have correlated sites separated by 2 independent in a ferromagnetic way, and they have done that in 3 separate bands, and that translates to these 3 separate lines. So they're taking 1 line out of 3, and there is this other anti-ferromagnetic paramagnetic ladder, which shows kind of this nice ladder geometry. And there are other 2, which, for example, this one is kind of eye candy, where you have interactions like ferromagnetic interactions between neighbors, but paramagnetic interactions between opposite sides on this circle. So on top of that, you induce periodic boundary conditions on this. And then if you look at the geometry, it's essentially a Mobius strip where the twist is guaranteed by these periodic boundary conditions. And on this other side, for instance, you have what looks like a cylinder.
Miguel, I have 2 basic questions.
Sure.
One is this, so in the cavity, is this level transition, is it spontaneous, or do you like induce by the assisted laser? Or?
Yeah, it's induced by this driving laser. That's essentially
okay.
this.
Okay. And second question is, what is rho again? Sorry.
Rho.
This rho I, rho j, like
those are
x, y, z.
these effective coordinates that you extract from the correlations. So essentially what you do is you measure these correlations and you assume that they are like Gaussian in the separation in some hypothetic or like hidden coordinate space.
Okay.
And then the way to extract them is by getting the singular value decomposition of this matrix of separations. And then I guess the number of dimensions would depend on like the rank of that matrix and so on and so forth.
Okay, thank you.
So basically, if I understand correctly, you have a complete graph, and to each edge, you associate a distance. Now, sometimes this distance is 0. Sometimes the distance is not 0, I guess. Right? Sometimes this distance is infinite. That's when there are no correlations. Right? And then sometimes the distance is finite. I see.
Right.
Thanks.
And then this experimenter group was like very interested in pushing this technique further, and they were collaborating with a theorist in Princeton named Steve Kubser, which I think died like 2 years ago or something. But he had a paper where he discussed ADS-CFT for p-adic system. So this weird, where you do like quantum physics in these weird fields, those p-adic numbers. But what they showed, I haven't read the whole paper, but what they showed is that if you have graphs that look like this tree, you see some of the features that ADS-CFT predicts for these hyperbolic surfaces. And then one of the results of this experimental study is that they were able to design interactions in such a way that the most natural coordinates for the correlations that they were finding were these well yielded a structure like this similar tree structure, and the correlations followed like the expected behavior in the p-adic distance of the lattice sites. So again, what they did here is they have a different pulse. So the pulse for this is given by, like, it has the strength of the separation raised to some power for these distances separated by a power of 2. So they are looking at like 2 adic systems. And then depending on the power that you raise, you either get a tree-like structure or you get a like what is essentially a one-dimensional system.
Sorry, Miguel, can I ask one question a little bit differently again? So
yes.
You just defined a measure of distance. You called the measure of distance as the log of the minus log of the correlator, right? So for that to be a metric, to be a measure of distance, it should have 3 properties. It has to be non-negative, which we're going to imagine in this case it is. It has to be symmetric. In this case, it is, because you took the absolute value. But then third one is that it has to satisfy the triangle inequality. I think for a generic structure, like for example, a complete graph, it won't satisfy any triangle inequality. That's where we do not have a geometry. We just have a graph with a bunch of distance, like quote unquote distance, bunch of numbers attached to each edge, right? To have a geometry emerge, you would like to have a particular form of correlations that satisfy the triangle inequality. Yeah.
Okay. Yeah, I think that's a valid point. I don't think they definitely. I don't know if that was the complete objective, or if they are ever looking for such a thing in for the metric that they're building. But yeah, it's a good comment on this. So yeah, then what they basically end the paper by saying that this nice tweak in one parameter and the kind of the redistribution or like the reinterpretation of the distances in terms of this p-adic norm gives rise to these tree-like structures, and this would like give a playground for experimentalists to test some of the claims of these ADS-CFT relation with the p-adic numbers. Okay, so that kind of ends that first paper that I was going to talk about, and now I will go into the simulations of hyperbolic space. So this is a very recent paper. It was featured.
Sorry, Miguel, can I ask, just say something? Already in the simplest example you discussed, which is no magnetic field, it's all-to-all connection, right? Everybody's talking to everybody. Atom is like a complete graph. Already in that case, there are some nice experiments you could do to compare with theoretical results. For example, there's a bound on there's a quote-unquote Lieb-Robinson bound on the complete graph, which is expected to show fast scrambler behavior, even in the simplest setup that you have. I think it would be amazing if there is some sort of an experimental demonstration of this. It's just a result in quantum mechanics, but it would be really neat to just do something like that. Maybe people have done that already.
Yeah, I think they in the paper they mentioned something along those lines, saying that this all-to-all interaction is effectively a fast scrambler. Yeah. Okay, so yeah, so this second paper will treat kind of this nice property that for the system that I showed at the beginning, which is kind of an array of superconducting resonators in one of the tessellations of the Poincare disk, and how we can treat this with a continuum theory. So there have been multiple implementations of hyperbolic geometry in atomic systems, and I will show you a couple of them. One of these is in nonlinear optics, where they design kind of different waveguides that make light follow what is like these hyperbolic trajectories. There was also another one in ultra-cooled atoms. So again, in both Einstein condensates, they are able to like replicate things like Hawking radiation, as in the study that I just showed, or even like build up like sonic black holes. And then the one that we will be talking about has to do with this implementation in circuit quantum electrodynamics, where the geometry is kind of the graph in which we're building everything. Okay, and then because this is a small slide on on the importance of hyperbolic lattices in circuit quantum electrodynamics. This is like a very nice kind of framework to do these types of analysis, because these CQED are very versatile. They do a lot of different things with them, because they allow for the like kind of you induce interactions between photons when they are placed in these resonators. You can couple different spin degrees of freedom of the photons, and you can explore, as this tiny image here shows, regimes where the system is in a disordered state, and you can trap photons in different ways. Okay, so first, let me start by defining what is the graph that we will be studying and what is the link geometry that we're going to give to it. So the circuit that I showed above is essentially, as I said, a series of resonators that are arranged in one of the tessellations of the Poincare disk. Specifically, they use the 7-tree tessellation, which is built out of heptagons, and each point has 3 neighbors. The tessellation has, like, formally, it has an infinite amount of points, but the graph that we will take will, like, cut the tessellation at a certain level, so we will only have a finite number of points. And the way that we're gonna kind of think about this is, instead of this series of heptagons, we're going to organize the points in concentric rings in the Poincare disk, like so. So the first heptagon is going to make the first ring. The ones that are after that are going to make a second ring, and we're going to make this these links according to the tessellation. So the Hamiltonian that they were using in the experiment, it looks like this. It is a nearest neighbor tunneling Hamiltonian, where you have like hopping between the connected sites in the graph. So this matrix A, what it does is, if you give it a function on the side J, what it gives is the sum of the 3 neighboring sites in side I. And this is what we will try to see, how to express this in the continuous geometry. So this continuum geometry will be basically, will live in the Poincare disk. Is the graph will shortly show that it lives in a disk of finite size in the Poincare disk, which is defined as the unit disk in the complex plane with this with the hyperbolic metric. And then we know that this hyperbolic metric is invariant under Mobius transformations, where what we essentially do is we translate, and then we rotate the point. And then because of this identification that we did with these concentric rings, any function that we define on the disk can be mapped to a function on the graph by just taking the side on the graphs and assigning it a coordinate in the disk. So what we will essentially do is we will study the action of this matrix I into functions on the graph as seen in the continuous geometry. So first, to get a sense of what this disk is, some of the properties of it, it is important to notice that the number of sides as we increase the number of rings will grow exponentially. So for the first ring, we will only have 7 sides. If we then add the other ring, which is achieved by essentially acting the 2 symmetry groups of the graph, which is the rotations by 2 pi over 7, and then the rotations in each side by 2 pi over 3. If you act with those like repeatedly with those 2 groups, you will start building up the different rings. So for the first ring, you only have 7 sides. Then the next one has 28 sides. So in total, you have 35, and you start growing and growing. And then eventually you can show that for L rings, you'll have this nice number as the number of sides. And then one
Sorry,
property.
Miguel.
Yes.
Is there any particular reason that this 3-7 tessellation was chosen? There are simpler ones.
Well, I didn't read the experimental paper, so I don't know why the experimentalist chose this, but everything we do here is generalized to any of the other tessellations. But I don't
it's
have an
more
answer
natural to consider like pentagon. Yeah, anyway.
Or even the triangles that make up the dual tessellation to this one could be a simple one as well. So another property that I couldn't really show, but will come in handy, is that this smallest ring is constrained to have this size for tessellation with p-gons and a coordination number of q. And for this specific one, this first ring has like this size. Okay, so now if we compute the distance between 2 points on this new arrangement of the tessellation of the graph, then the distance between any 2 points using the hyperbolic metric is going to be given by this number, and we will shortly, I think, see why this is. And then what we essentially want to do, if you remember, is seeing how this matrix A acts on different functions. And to see how that is done, one thing that we would like to do is to be able to describe how this A function acts on this A matrix acts on a function f, and express that only in terms of what the function does to a single point. And to do this, we will use the symmetry of these Mobius transformations to take the point that we're interested in and moving it to the center. And by doing this, so you have your point of interest, it's CA separated by D0 to these 3 points like this. And then if you move it by this Mobius transformation, which essentially moves the point ZI to 0, you end up with these 3 neighboring sites that are now separated by a distance h. But these 3 points are expressed in a very simple way because they are just 2 pi over 3 separated from each other, plus some arbitrary phase, some phase determined by the point ci. But they are expressed in a much simpler way than what the original points are. Nonetheless, since this transformation leaves a metric invariant, then the distance between any one of these points and the origin has to be D0. So if you plug in, if you plug in the expression that you have for each one of these points into the formula for the distance between 2 points in hyperbolic space, what you end up showing is that the distance from the origin of those transform points is equal to the hyperbolic tangent of the distance between 2 points in the original graph. So the 3 points after the Mobius transformations are expressed in this fashion, where h is equal to the hyperbolic tangent of d0. Now, what we want to do is make a formal expansion of the function of the matrix A acting on the function f, make a formal Taylor expansion in H. So what we want to do is to do a power expansion in H, which might seem unjustified since H is fixed by the geometry, but we will see that it gives kind of a good approximation to a very like a smooth function. So this point, if you invert the Mobius transformation, you can express it in terms of the W, these Wi's like this. And so A acting on F is essentially this sum. Now, if you take derivatives with respect to H, you have to like do the chain rule multiple times. You end up with expressions like this for each one of the points, and then we're going to do up to order 2, and so you end up with this expression for the total derivative. Now, if we consider the fact that if we sum over these phases, so the phase is essentially that chi I coming from the initial point plus the separation of pi over 3, it is easy to see that the sum of those 3 W numbers gives 0, as well as the sum of the squares of those 3 W numbers. So if we take each factor as before and we add them together using that simplification, we see that the linear term vanishes, and then there's only a second order term. And then the expansion looks like this. Now, one interesting thing is that this second order expansion gives rise to the appearance of this Beltrami-Laplace operator in the disk. So if we replace what this is in terms of this derivatives, what we find is that the action of this A matrix on any function f is given by this. So the appearance of this Laplace operator is independent of the tessellation that we find. These coefficients are related to the coordination number of the tessellation that we're in, and this h, the value of h, will be different for each for the different p's that we choose. But this is like the general form for the expansion, plus some order 3 terms. So how bad is this approximation? Surprisingly, it's not that bad. So what we see here is that if we choose the function f to be the cosine of pi times the distance to the origin, here they show like what is the different values for the function. So
sorry, Miguel, can you remind us what this function f is?
Oh, so it's an arbitrary function. So far for here, it's just an arbitrary function. Eventually, it would be like our creation and destruction operators when we translate this theory to the continuum. But so far, it's just an arbitrary function.
So yeah, I guess I'm not. Yeah. Okay. Sure.
So yeah. So again, this expansion in powers of h seems unjustified since h is finite, and the limit, well, it has no relevance in the geometry. But as we will see in the paper, they go into details as to why the third order terms will not be very relevant in the case where f is a destruction operator. But here you can see like how the approximation evolves as you change h and how it is not that far away from the real value. So here the empty points are the real value of the function, the squares are the third order expansion, and the line is the second order expansion that we just derived. Okay, so now that we have tackled how A acts on functions, the next thing what we want to do is see if we can turn sums over the graph into integrals on the disk. And we can do that, and I'll show you 2 ways to do that. Sorry, this is a little small, but essentially what we can do is we can do a finite element analysis of this. Basically, you take this integral, and if you break it down into a sum where A is the area of the dual of this triangle, which makes up the dual graph for this graph, and which itself is another tessellation of the space. What you can show is that this sum is very close, it's close to this integral. And in fact, the area of each one of these triangles is independent of the side. And it reduces to these difference between pi and the sum of all the interior angles of those triangles, which for a general tessellation, it's this expression, and for the tessellation of 7, 3, it has just this 2 pi over 7 value. Now with this, now that we know this, if we fix f to be 1, which on the left-hand side would be just counting the number of points, and we plug that into our formula, we'll be able to determine what is the size in the Poincare disk that this graph will occupy, and it turns out that it follows this relation with the number of points. Another way, which I thought it was kind of a clever way to show that integral formula holds, is by rearranging the sum in a different way, where you identify points that are connected via this rotation by 2 pi over 7. So what you essentially do is you go to your graph and you take groups of 7 points, which are related by these rotations, and then you perform, well, one of the things is that they are at the same separation from the origin, so they will have the same radius. So if you take a function that is independent of the angles, this sum is just splits into 7 times the sum over each one of these groups. You can see that by defining this like auxiliary variable, which is invariant under Mobius transformations, you can re-express this sum as this integral here. And again, L is fixed by matching the number of points. And then if you add a function that is not, that it doesn't have that trivial dependence on the angle, what you essentially do is you replace the sum over these different sides by the Riemann, so the sum over the different sides is replaced by the Riemann integral, and you recovered that same expression for the integral. For the sum equals the integral. Okay, so now that we know how to express sums and the action of A over any functions, one first example would be to treat the Bose-Hubbard Hamiltonian. So it is essentially this Hamiltonian. You have this hopping term between neighboring sides, chemical potential, and then some type of potential depending on the number of particles in each side. So by applying the rules that we derived before, we essentially replace the sum by this integral and replace A by the corresponding expansion in terms of h squared. What we find is that we can describe this Hamiltonian by this like continuum theory if we define these new operators as this in terms of the operators on the graph. And we extend just A, Z to some function that coincides with these A operators at the lattice, at the points of the lattice. One of the things, one of the details that we skipped was looking at boundary terms, because if you see the boundary terms, they have a correlation number of 2. So some of the action of the A matrix in them is slightly different, but by rearranging, you can show that you recover this extra, this 3 times the function, the value at CI plus this Beltrami operator, minus like the value of the function in this extra term outside the graph. But if you expand this as if you expand this in powers of h to first order, you will get this, which you can add to to the definitions of the functions, but you notice that it will be linear on F. And since we're interested in F being a destruction operator, if we act with this Hamiltonian on any state on that graph, since this side is outside the graph, acting with it on the wave function will just give 0. So any contribution coming from these boundary terms, in principle, goes away. But treating more formally and including the boundary terms is like some future research that the authors have, like it's on their plan to tackle these boundary terms. Okay, so now that we have like a Hamiltonian in the continuum, the next task is to go through some Spectre theory of the continuum and the theory of the Beltrami, like the spectral theory of the Laplacian in the hyperbolic space is well known. So we know that the wave functions, that the eigenwave functions have these eigenvalues and they have this form. And similarly to Euclidean space, we can do like an expansion in terms of special functions like this. So like in terms of partial waves. In this case, the partial waves will be given by Legendre polynomials of the special kind. In this, which would be like Legendre functions in this case. And they can be found by using the inner product in the hyperbolic space on top of this function. And then if you plug in, or alternatively, you can plug in these ansatz for your eigenfunction, and you will find that the G functions follow the Laplace equation, the Legendre equation. So as a first application of the theory, so there are two applications that we'll go through. One is determining the ground state and the first excited state of this theory and comparing it with some results from graph theory. And then the second one will be exploring the correlation function, both in the discrete graph and in the continuum theory. So again, this is the Hamiltonian that we start with. And in terms of determining the eigenvalues in the graph theory, in the graph, so this quantum mechanical theory, A is like a very sparse matrix, so they're very efficient algorithms like the Langshaw's theory that we studied last time that allows you to diagonalize this matrix. And for a baby case of L equals 1, this is just a 7x7 matrix where the ground state will have an energy of -2. But you saw that adding the next ring will increase the size to 35. So then it's a 35 by 35 matrix, and this grows exponentially. So it becomes intractable very fast.
Sorry, Miguel. So if I understand correctly, what we are doing right now is we are looking at Bose-Hubbard model on a 3-7 triangulation of the hyperbolic disk, and you're solving the Schrodinger equation for this Hamiltonian, which is like just simple Bose-Hubbard, right? Just ij are all the links of the graph. Okay, yes. So you've not allowed any chemical potential.
Yeah.
Okay.
Right. Just the tunneling.
So what is known about this the vacuum of Bose-Hubbard and this this geometry? Discrete geometry.
I don't know. I don't think I follow your question, but
so take Bose-Hubbard model. You mentioned you've been discussing this particular triangulation of the Poincare disk, a particular one, right? So put the Bose-Hubbard model on this, and what is known about the ground state energy, say in the limit of large number of sites, like the quote-unquote thermodynamic limit. What is known?
Oh yeah, I guess some of your questions can be answered as in the next slide. I have some like evolution of what is the gap for different number of rings.
Yeah. Okay, so that's what I was asking. Yeah. Okay.
And yeah, and one of the objectives of this paper is showing that by analyzing the continuum theory, you have like a more efficient way of computing those things. Okay, so yeah, for the first case, the ground state energy is -2, but there are some graph theoretical results that have put a bound on the ground state, that they know that the ground state energy has to live in this interval. On the other hand, for the continuum operator, we have that it will be given by this operator. So the energies based on what we saw before are going to be like this -3 plus 3 orders of the eigenvalue of the Laplace operator. If you take L going to infinity, so an infinite number of rings implies that we are approaching more and more the limit of taking the whole disk. We know if we do this, then the smallest k that we can take approaches 0. So we have a lower, like a minimum for the ground state energy in the case that we take the whole disk, and that is going to be given by this, which falls right in the bound that the people from graph theory have given us. Now, in the case that we have a graph that has one like a finite number of rings bigger than or equal than 1, then what happens is that the way that we're going to find the spectrum is by essentially requiring that the wave function has a 0 at the boundary. So we're doing like a hyperbolic box, if you want. So here again, like we require that the wave function is regular at the origin and require this boundary condition. Then the eigenenergies are going to be given by the location of the zeros of these Legendre polynomials. So for the first zero, having two different azimuthal numbers, the expression for the eigenstates for for the eigenenergies for the ground state and for the first excited state are given by this, where these k I have different have a different dependence on the size on L and in the number of lattice points. So in the limit of lattice rings, rather. So in the limit where L goes, it grows very large, is very large, so that we can approximate the number of points by this power of the golden ratio. Then what we find is that the ground state energy looks like this, and the first excited state looks like this. So with this, now we can compare what is known for the eigenvalues of that matrix A in the graph and compare that to what we find in our theory. And we see that in the limit of large L, so starting from like L equals to 4, moving on, the correspondence between the theory in the graphs and the theory in the disk is quite good. And we actually see here, like comparing three things. One is the empty dots correspond to the eigenvalues in the continuum theory. The solid dots are the theory in the graph, and the line corresponds to this asymptotic limit. So you see that it kind of kicks in at around 6, will like all the eigenvalues coincide. And then another thing that they did, like in order to see how well other eigenvalues were matching, was computing the partition function for only the negative energy modes of the graph theory, because the continuum theory will only have negative energy modes. So if you restrict to that and calculate the partition function that's essentially the free energy as a function of the inverse temperature, you see that they align pretty well. So I believe like blue is the graph theory and red is the continuum theory.
So sorry. So L is the number of layers.
Yes, number of rings.
And how does the gap? So the gap is closing as L goes to infinity, right? How does it close? Does it close polynomially in the continuum? Well, I guess, yeah. What does it? I'm a little bit confused as what does it mean for. Well, what's the meaning of L in the continuum theory? I guess you're saying it's a.
Well, it is the radius, right? The where, like.
I see. Sorry, I see. Right.
It approaches 1.
Do they mention how it closes as a function of L? How the gap closes?
No, but I guess you can take like the difference between these two dependents on, bless you, on L is right here.
So it's closing polynomially,
Like,
as one expects from the symmetries of the hyperbolic space. Okay. But this is like quantum mechanics of it's a one particle Hilbert space. It's quantum mechanics in hyperbolic disk, right? This is the physics of it and a discretization of it. I see. All right, thank you.
okay. So the next result would be to study the correlations, and in order to do that, what we're interested is in the Green function. So for the discrete theory on the graph, it's essentially this operator as the resolvent of H at this energy, and then what we will do is we will use this handy identity from this path integral, where you can obtain the inverse of the Green's function basically as a path integral of the two correlation, of the 2-point function. And then we can use our mapping from functions on the graph to functions on the disk, and use our expression for sums in terms of integrals to correlate the Green's function in the graph to the Green's function in the disk. And then if you follow this calculation, which is just a change of variables, essentially, you will find that they are related by this factor, which includes the distance between the neighboring points, this H parameter. And then the energy noticeably is also scaled by that H parameter, and is shifted as well. So now if we compare what the correlation function gives, then the diagrams on this side, by the size of the dot, they represent the value of the norm of the correlation, and the color gives the sign. So here, this one is for the lattice, this one is for the continuum system, and these two panels are given for different energies, but they are the same. And then the graph over here, what it does is for each value of the separation, it takes the average of all the possible sides. So we fix I to a specific value, and then this is a function that depends on J. And then what you do is you take the correlation for each point that is separated by this much, and you take the average, and that's how you obtain these graphs. And then the inset, what it gives is a different number of layers. So for the big, for the graph, like the big graph, and these kind of these pictures over here, they are taking 6 rings, but for the inset they take 3 rings. And then one thing that is very nice is that as you increase the number of rings, then these graphs collapse into a single curve, which denotes the emergence of the conformal symmetry on the graph. So yeah, then I give you here like the value for the two energies that they are checking this out at. This one is a complex energy, and the first one is below the ground state. And then some future kind of directions that they were planning on taking this study was to, well, first was studying these boundary terms that they have left out, and see what that can tell them in like ADS CFT. This is a very nice playground to test ideas of holography, and there are some like error correcting quantum codes that can be implemented in the hyperbolic graph. And then this would essentially give a tool for a more efficient computation of quantities in this type of geometries. And then they also mentions that this would eventually give a platform, or it is a platform for the simulation of gravity in 2 dimensions. And yeah, that essentially closes the presentation. Thank you very much.
Thanks so much, Miguel. Are there questions for Miguel?
I have a question. Could you go back to 2 slides back? So when you make the statement, this slide, yes. So when you say like the emergence of conformal symmetry, like, how do you see this? Maybe I couldn't understand like how you get this. How do you see the conformal symmetry? Can you say a bit more?
Yeah, I guess I'm not that well versed into why the collapse into a
I think
symmetry.
Kichira probably, I mean, at
Yeah.
the very naively, one thing to notice is that the 2-point correlator as a function of distance is falling off polynomially. I suspect that's a polynomial, and it's a, sorry, I said parallel. It has a parallel behavior, and then you would identify the exponent with the critical exponent, right?
Okay.
But it is a statement that just follows from the symmetries of the hyperbolic disk, right? You expect
Okay.
that.
Okay.
Yeah.
So you would get the conformal dimension for the power.
Right. Right.
Okay. Okay. Okay.
In the
Thank you.
continuum limits, right?
In the continuum. Okay. 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 Thank you.
Any other questions?
Can I ask a question?
Sure.
So in sorry, like usually we say that the signature of holography appear not in 2-point functions, but maybe higher point functions, because 2-point functions are kind of universal. So have any of these people have talked about like higher point functions? Or
No, they did not discuss that in the paper. They only talked about 2-point functions, and the main result of the paper was the 2-point functions coincided. But like those types of tests for holography are like what their future research will tackle.
But Modesti, I think the idea is that this is just quantum mechanics on hyperbolic disk. We don't quite expect this to be holography, right? I mean, the connection is at the level that we expect connections between quantum mechanics on hyperbolic disk and holography, which is, I mean, there are many steps in between. Yeah, so even if you calculated higher point functions, I don't think that we expect much to look like, we expect it to look like something like holography. In particular, the time evolution here, I insist it's quantum mechanics, it's like single particle, because they are solving the Schrodinger equation with this Hamiltonian. There's no field in the bulk, there's no Klein-Gordon equation or something. It's just Schrodinger equation. It's non-relativistic quantum mechanics, single particle.
sure. Yeah.
Any other questions? I actually have a few questions. I think the beginning of the talk in the first few slides, remember when you were discussing this model with some gradient magnetic field and a bunch of atoms on a line. So experimentally, how many atoms can they squeeze in there? What's the limit?
I think that they said that each one of these red dots has like 10⁸ atoms, and then they have 17 points in the ladder.
17 points, I see. So, and another thing, a question that I have is that, so you look at 3-level system. 3-level system in principle could have, so you only looked at bipartite interactions, right? So one goes down, one goes up, right? So
correct.
If you have 3 levels, you could probably perhaps tune it to have tripartite interactions, right? One jumps down by jumps up by delta E1 plus delta E2. Another one goes down by delta E1. The other one goes down by delta E2. Right? It's imaginable that you would tune a tripartite correlations. and four-partite correlations, and so on and so forth. Such things would correspond to hypergraphs. Now, why do I say that? The reason I say that is that we expect the behavior of a complete graph to be very different from something like a four-partite interaction. So this hypergraph with all-to-all four-partite interaction is something that mimics some sort of a SYK structure, which is, you know, is supposed to be a theory of quantum gravity, blah, blah, blah. So it would be fascinating if people can push this further and engineer all sorts of, like, well, it's kind of funny that they already have all-to-all, like, for free. You get all-to-all for free from the cavity.
Yeah.
That's already very fascinating, because there are calculations that have been done or bounds that have been found, but there are no experimental demonstrations of those bounds. It would be really nice to look at fast scrambling in these models. But even beyond that, if you introduce like these n-partite interactions, it would be just very fascinating to see how it works. Yeah, I think it's a potentially very promising direction.
Yeah, this is a group from Stanford. I think is the one that's behind this. I owe everyone an apology for not putting the references properly, but yeah, this is from a group in Stanford.
Any other questions?
Sorry, Miguel, is this three-level system? So like when you, just so this is simple AMO question. So you start from 0 state. Are you exciting to some quasi-static stable state on like whatever higher, and then you induce the decay to 1 and -1? Is that how it works?
No, well, are you asking how do you get the tree levels?
No, actually, how does this transition work? So like starting from 0, how do you get to state 1, and how, or how do you get to -1?
Oh,
I was expecting this something like the Raman scattering. Like you have three, in that case, you have three-level system, and you excite it to quasi-stable state, and then you induce you shoot the assisted laser, which you induce the decay from that state with some detuning. Is this a similar thing, or is this different process?
I don't have a good answer for that really. I'm sorry, I don't know how they populate those states.
Okay. Thank you. No problem.
Any other questions? If not, let's thank Miguel again for the wonderful talk. Thank you so much. It was very clear. It was really, really good. Thank you.
Thank you.
We should chat more about this. Hopefully, I'll be back in the beginning of January, and we'll chat more in person.
Sure.
Yeah. Thanks so much for the talk.
Okay.
And thanks everyone for coming here. Have a great evening.
Thank you. Bye.